Okay, we are talking about the fundamental theorem of calculus today. And there are two definitions for your fundamental theorem of calculus, okay? The first definition for both of these is that f is continuous on a closed interval from a to b, okay? Anytime you see that bracket here, that's how you say that, on a closed interval from a to b. So we are given a function, g of x, that's equal to, this is the integral or antiderivative from a to x is how you read that, of f of t dt, then the derivative of g is equal to f of x. Now, that's a lot of notation that probably means not a lot to anyone out there. But basically what it's saying is that this thing right here, this thing right here is my integral or my antiderivative, okay? And this right here is my derivative. Integrals / antiderivatives and derivatives, those are inverses of each other, okay? This blue thing that I highlighted here also, this is the accumulation function. And what that means is it's just like how much area underneath the curve do we have, right? That's what the integral is telling us. So the accumulation function is the blue thing, and then we know that derivatives and integrals are inverses of each other. Okay, the second part of this fundamental theorem of calculus, or FTC for short, is your integral from a to b of your function f of x is equal to capital F. Note the difference here. Capital F is the antiderivative of lowercase f, your function. So you're taking the antiderivative and evaluating it at b, and you're subtracting the antiderivative evaluated at a. We're going to see this notation a lot moving forward in this class. Okay. I also wanted to say here, this a, that is a constant. Okay, and this x up top is a variable. Okay, so this second part of that theorem right there, if you look just right down below, this net change theorem, this is the exact same thing as above, okay? This formula right here is the same thing from up above, so it's that fundamental theorem of calculus, and then all we do with it is we change it a little bit so that way we can figure out one of these values, okay? If we're given our starting amount of f of a, and we can find the change between my a and b value on the x-axis, I can find my end amount, okay? So all we did from this formula to that formula was solve for f of b. Okay, normally we're going to write it like this, but this is the same thing, it's just solved for f of b. Because we're going to be given a lot today. We're going to be given a starting amount, and we're going to be given this value to find on a graph. So that way we can find out what our end amount of our area underneath our curve is. Okay? All right. Now, I'm going to add a picture to the next slide here. If you guys want to add it on there as well, you can, or you can just kind of pay attention to see how this kind of works. So, this is an example problem, one of the ones from your AP College Classroom, or AP Classroom, you guys can see. If you ever want to watch those videos, they're up there for you. If we are evaluating a function given an integral, okay, where g of x is equal to 0 to x of 2t dt, and we've got this graph here. So this graph on the right-hand side is just the line y equals 2x, okay? Do you guys agree with me? That line y equals 2x, okay? Now what we're going to do is we're going to find the area underneath the curve on different segments. The first segment that we're looking at is we're going to plug in 0 for x. So I'm looking at, if I plugged in 0 for x, of 2t dt. Okay, so that means underneath this curve at 0, is there anything underneath from 0 to 0? Is there anything underneath that? No. So your area underneath the curve is just 0 there. Now if I change it and go to 1, if I go from 0 to 1 of 2t dt, I chose the wrong color. I meant to do blue. That's okay. We'll change this one to red. Okay. If I were to draw that straight down, the area underneath that curve, this x value is 1. I know that that line is 2x. So my height of this triangle would be what? 2. So the area of this triangle would be 1. 1/2 base times height, right? So my area here is 1. Okay, then what if I found the area from 0 to 2 of 2t dt? So if I were to draw this line down, I want to find the entire area of this triangle now. So my base would be 2. My height would be 4. So 1/2 base times height gives me an area of 4 for this one. And then lastly, if I did from 0 to 3, ooh, that's a real bad color to see. Let me choose a darker one. From 0 to 3 of 2t dt, if I were to find the area of that big triangle, I would have a side length of 3 down on the bottom. What's my height going to be of that triangle? 6. So 1/2 base times height would give me 9. Well, yeah, and then divide by 2. Okay? So, is there a relationship between my x values and my g of x values? Yeah, what's the relationship? They're x squared, right? So technically, g of x is x squared. Do you guys agree with that? Okay, if I asked you to tell me what the derivative of g of x is, so g prime of x, what's g prime of x?
2x.
Equals 2x. Interesting. Wasn't this line 2x? Oh. So if I look at that formula from the previous page, our g prime of x, this formula right here, g prime of x, is f of x. Okay? Where you take this value x and you substitute it into this function to find your f of x value. Because this is technically our f of x, so this would actually be just 2x like I just said, right? If I took the derivative, that tells me my function, and that gives me my function of 2x from that original integral that we were given up there. Okay, kind of cool. So we're going to go, from one to the other, and then we can go backwards by using the integral. Okay, but today we're still going to focus on looking at graphs, finding areas underneath curves using this idea before I show you guys how to use a bunch of formulas to find these integrals as well. Okay, and we're also going to use our calculator today, so if you don't have your calculator out, grab that out because I'll show you how to plug this stuff into the calculator as well. Okay. All right. Okay, so we are looking at net area underneath this curve that we're given. This curve is our f of x function. Okay. We're given this formula. G of x is equal to the integral from 0 to x of f of t is equal to dt. So what we're going to do is we're going to plug in these x values into this function. So I'm plugging in 0, 1, 2, 4, and 6 into where x is right there. Okay. So if I plug this in here, this is the integral from 0 to 0 of f of t dt. So I want to know, what is the area underneath the curve from 0 to 0? Is there going to be anything underneath there? No. Anytime we go from 0 to 0, it's always going to give us 0. Okay? There's nothing underneath the curve if we haven't moved. Okay, g of 1. So I'm going to look from 0 to 1 of our function that we're given. So if I look on our graph from 0 to 1, what is the area underneath that curve? 1. right? 1/2 base times height gives me the area of 1. So my answer here is 1. Okay, g of t goes from 0 to 2 of f of t dt. So if I look at my graph, I'm going all the way to 2. So I'm going to add in this area, which is also 2 in this case. So add those two things together, and I'm going to end up with 3. So your area is 1 plus 2, which gives you 3. Okay, g of 4, plugging in that formula from 0 to 4 on our graph. I want to include this area right here that I just highlighted. And it says in the instructions there that it's a quarter circle. So if I wanted to find the area of this quarter circle, I would have 1/4 times pi r squared, where my radius is 2. So it's the area of that quarter circle. Pi. So this would be all the stuff previous. So 3 plus pi would be your answer. Okay, lastly, g of 6, we're starting at 0 and going to 6 of f of t. So I'm just going to add in this piece underneath the x-axis. And anything that's below the x-axis has a negative, right, value. So what's that value underneath the curve going to be?
Negative pi.
Negative pi. So I'm taking the stuff I already had up through 4, and I'm adding a negative pi. So what's my area going to be under that curve? 3. Okay, so the area that we've in total accumulated from 0 to 6 is positive 3. Okay, we added all the stuff up top, subtracted the stuff on bottom, and gave us an area of 3 all the way from the left to the right. Okay, now for the next 3, we're going to find the derivative of g. So if you remember from the previous page, the derivative of x is equal to f of x. Okay, so g prime of x is equal to f of x. So g prime of x, so g prime of 1 is equal to f of 1. And aren't we given the graph f of x? Yeah. So can I find out what f of 1 would be? Yeah, that blue line there tells me those values at each point. So if I look at 1, what's my y value at 1? 2. So f of 1 is equal to 2. G prime of 4, we're looking at, okay, well, when is my function equal to 4? 0. And lastly, at 6, when is f of 6 equal to negative 2? Any questions on evaluating either of those, the derivative or the regular function? Not too bad? Okay, sketching graphs, everyone's favorite thing to do ever. Okay, we want to sketch a possible graph of what g looks like in this coordinate plane, and we're going to need to think about what the second derivative looks like as well. So, reminder for ourselves, okay, we already know values of g on the graph, don't we? We know what g of 0 is, we know what g of 1 is, we know what g of 2 is, all the way up to 6, right? We found those things. So I'm just going to write that in a table down here of our x values and our g of x values. So that way we know those are points we already found that we're going to plot on our graph. So I've got 0, 0, 1, 1, 2, 3, 4, 3 plus pi, and 6, and 3. Those were all given to us up above that we just found. So I'm going to graph these points on the graph, and then we'll talk about how are we going to connect the lines, because we can't just like do a dot to dot here. We got to talk about what's happening in between each point. So So 2, 3. 4 is just going to be a little bit above 6. And then 6, 3. Okay. So our hint is to find values of g double prime of x. Now if we go back up to the function up top here, real quick. Okay, remember this is equal to my f of x function, right? This is my f of x function. Well, my f of x function is the derivative function, right? G prime of x. So if I wanted to know g double prime of x, what would I have to do with f? Take the derivative as well. So if I take the derivative of this graph and find those values, what's that going to tell me about my g of x graph?
Concavity?
Yeah, concavity, okay? The second derivative tells us concavity. So let's write ourselves a little note about that. Tells us concavity of g of x. And technically the first derivative tells us whether something's increasing or decreasing, right? Just kind of a reminder from last unit before break. Okay, so looking at these blue lines here, I'm going to look at what are the slopes of each of these values. So from 0 to 1, all of these slopes are going to be what? Positive slopes. What about from 1 to 2? What are those slopes? 0. They're horizontal. And then I go from 2 to 4. All of these slopes are going to be negative. And then they continue to be negative slopes, right?
All the way down?
All the way down. Okay. So if I think about this as a number line here, I'm just going to draw a little number line with these points of 0, 1. Oops. Here, I'll put it down here, actually. I'll put it down here. We should have enough space down here. So this is our g prime of x, tells us our concavity. So we've got 1, we've got the value 2, and then 4. And then all the way to 6. Okay, so the slopes to the left of 1 were all positive, which means, are we going to have a concave up graph or a concave down? Concave up. When it's positive, it's concave up. In between 1 and 2, my slope was 0. So is there going to be any concavity at all?
No.
Nope. We're just going to have a straight line connecting those 2 points from 1 to 2. Between 2 and 4 and 4 to 6, all of those slopes are negative. So this entire section of the graph is going to have concave down. And now I can just connect all these dots on my graph with that concavity information. So between 0 and 1, I'm going to have a slight upwards parabola there for concavity up. Between 1 and 2, I'm just going to have a straight line between those two things. And then from 2 to 6, it's going to be concave down the entire time. So concave down, you're going to have an upside down parabola, something like that. Okay, remember, this is the graph g of x that we just drew. But we used the second derivative to tell us where our concavity is going to be. Is it going to be positive, so it's going to be up, or is it going to be negative, and then therefore the concavity would be down? Okay. Now we're going to be given a graph f prime to find values of f. Okay. So this function on the left is on a closed interval again, with f of 0 being -3. So this is going to be our starting point. Okay, you're going to be given a value for a bunch of things today to find our other value. So we're given the first derivative on the left-hand side. We've got a semicircle and then a line segment. So on the bottom left of your page here, I'm just going to add in the formula from the previous page so that you have it on this page as well. But your formula is f of b, that's your end amount, is equal to f of a, which was your starting amount, and then plus the integral from a to b of f prime of x dx. So this is what we call the net change between where you start and where you end. So this f of 0, this is my starting point. This is what we are given. Okay, so I want to find f of negative 4. And in order to find f of negative 4, I need two other pieces of information. I know my starting value, which is this value here that we're given, negative 3. And then since we're given a graph, I can figure out what my change is from A to B on my graph. So let's plug this into the formula and see how this works here. So this f of negative 4 is equal to f of 0 plus 0 to negative 4 f prime of x dx. Okay, well, we know what f of 0 is. F of 0 is actually just equal to negative 3. So this equals negative 3 from our given, yep. And then we got to change this integral here because this integral, if we look at like, a number line, this it says I'm going to start at 0 and then go to negative 4. Does that make sense if you're like looking at a graph? Do I start at 0 and then go to negative 4? No, I go the opposite way, right? I start at negative 4 and I go to 0. So I need to flip that around. And when I flip that around, it's just going to change that sign to a negative. So this becomes negative 4 to 0 of our derivative. Okay, so this changes to a minus, and then your values flip around. If it doesn't make sense in terms of like your x-axis, you want to read it like a book from left to right. Okay, now we can just evaluate that. We're looking at the graph from negative 4 to 0. So from negative 4 to 0, I want to find the area underneath the curve. Back to geometry, how am I going to do that? How do I find that area there that I shaded?
Find the rectangle, subtract half the circle.
Find the rectangle, subtract the circle. That's exactly right. So my rectangle area is 2 times 4, which is 8. And then if I subtract this semicircle, what's the area of that semicircle going to be?
It's pi times the square root of 2.
So let's see. 1/2 pi. What's my radius is 2, so 2 squared.
2 pi?
2 pi. So 8 minus 2 pi is technically the area underneath the curve here and here. And I'm just going to take that expression and I'm going to plug it in to my integral. So now I have negative 3 minus, be careful you don't make a silly algebra mistake, we have to subtract the entire quantity of 8 minus 2 pi. Which does simplify to give me negative 11 plus 2 pi. So that is our f of negative 4 value. It is equal to this negative 11 plus 2 pi, or if you like plug that in the calculator, it's negative 4.717 approximately. Okay. Let's try out the next one. F of 3. Again, we still are given the starting value of f of 0. So I'm going to start with f of 0, and then I'm going to add that with the integral of the net change from 0 to 3. So 0 to 3 of my derivative function. Okay, Now, do I need to change the order from 0 to 3? Does 0 to 3 make sense in terms of an x-axis? Yeah. So we can leave that, and now we can just put our information in. F of 0 is negative 3. So negative 3, and then I'm going to add the area under the curve from 0 to 3. So look at my graph. From 0 to 3 means I need to find this area, and I need to add that to this area. Okay? You always find the area to the x-axis. I had someone last class trying to find the area of like this whole triangle. That's not what you're trying to find the area of, okay? You're finding the area to the x-axis. When it's above the x-axis, it's positive. When it's below, it's negative. So my area up top, that gives me 1/2 base times height, which is 2. And then the area down below would be 1/2, right? But if it's below the x-axis, it's technically negative. Okay, so I'm going to add those two values to negative 3. So I've got negative 3 plus 2 minus 1/2. So if I simplify that, I get negative 1.5. Okay, questions on those two? Okay, we got one more problem to do, and then you guys have some time to work on your homework. This one last problem does have like not 6 parts, but kind of 6 parts to do though, okay? Okay, last one here. Using the graph f prime of x to find absolute extremas. So this is your f prime of x graph. We good? We are given again that f of 0 this time is 3. It's not always going to be f of 0. It could be like f of 7 that you're given or f of 3 that you're given, okay? Which means then that your value is going to change on the bottom of your integral. So I've got 4 line segments, 1 semicircle there in the middle, and it's asking us to find the absolute maximum value of f of x over the closed interval. So we got to think back to last semester. How do I find absolute maximum of f of x if we're given the derivative? What's 0? When is the derivative 0 or undefined? Those are the points we have to test. We called that, anyone remember? Starts with a C. Close, not quite right. We called it the candidates test. Okay, but yes, we have to use the critical points technically. So the points that we're going to test, we're going to write a little note here to ourselves, is when we are finding the derivative to be 0 or undefined, and the endpoints. Okay, finding the absolute maximum is technically using the candidates test. And the candidates test says we have to find when the derivative is 0 or undefined, and then we also have to test the endpoints. And we're trying to figure out where is the maximum value at on those points. Okay, so it's equal to 0 or it's undefined at what x values? If this is my derivative graph, where is it equal to 0?
-4, -2,
Nice.
5.
That's exactly right. Those are all my values of where it is equal to 0 or undefined. So we're going to test the points x equals -4, -2, +2, and 5. And then my endpoints that we're going to test are x equals -6, +6. At one of these 6 values, we are going to have an absolute maximum occur on f of x. So to help us organize a little bit, I'm going to write a little table here where my x's are on the left-hand side. And I'm going to have -6, -4, -2, 2, 5, and 6. And then we're trying to find f of x. So f of x is going to equal our f of 0 value that we're given. Again, that number could change. It could be like f of 5 or f of 2 that we're given. And then I'm going to add that with the integral from 0 to x. That number on top is going to change of my derivative graph. So I'm going to do probably like 2 of these with you guys, and I'm going to let you guys do the rest of them by yourself, and I'll kind of walk around and help if you need it. But for -6, if I'm finding -6, I'm going to plug in -6 anytime I see x. So my f of 0 that I'm giving up above was 3. So I've got 3 plus the integral from 0 to -6 of f prime of x dx. Now, does 0 to -6 make sense? Nope. So we need to flip it. So this is actually going to become 3 minus 0. Oh, no, sorry. -6 to 0 of f prime of x dx. So again, I just flip-flopped these 2 things and I changed it to a negative. Okay? So when I look back up here in my graph, I'm looking from 0 to -6. Or sorry, up backwards. -6 to 0. I'm going to draw my area here, highlight those in. I need to find the area of all this stuff. Okay, so if I found the area on the left side, this triangle right here, that's 1/2 base times height. So my area would be 2, right? What's my area of this triangle right here? Base, yep, so 1. And then this one underneath here is technically like a quarter of a circle. So that would be like 1/4 pi r squared. My radius is 2. Yeah, it's just pi. Okay. Now, if it's below the x-axis, that area is negative that we're accumulating. And if it's above, it's positive. So if I plug this stuff back into my formula here, I've got 3 minus the entire quantity of all those things added together. So -2 plus 1 minus pi, which is all going to simplify to give me just 4 plus pi. I almost made a silly mistake there. 4 plus pi. Okay. Questions on how I got the -6 value for f of -6? Okay. Then I'm going to do f of 2 with you as well, and then I'm going to let you guys try out those other ones on your own with me walking around helping you guys if you need it. But if I did f of 2, I'm still going to have 3, but then I'm going to have from 0 to 2 of f prime of x dx. Okay, so 3 is going to stay there, and then let's go look at our graph. From 0 to 2, what is the area there going to be? Negative pi. So this is just going to be 3 minus pi. Okay, between those 2 that we just found, which one is larger? Which one's the maximum value so far? The first one at -6, right? Okay, so now I'm going to let you guys have some time. Try out finding the area underneath the curves of those other 4 to find out those values at that point to see which one is going to be our absolute maximum, okay? And then I'll come back and make sure we all got the same answers before we talk about our final kind of conclusion for this question. Okay, do we all agree with these answers? Yes? So where is my maximum occurring at? Which one's going to be the largest value? At -6, right? So our absolute maximum, we can kind of write this with a conclusion sentence here with all the information in one. Our absolute maximum value of our function f of x is 4 plus pi at x equals -6. Okay, so you did all that work, you got all that practice, but your answer was actually the first one that we found. Okay, any questions on this stuff? Okay, then the last thing that I need to show you guys is on your homework for the circuit. specifically the accumulation circuit. If you would go ahead and pull that out, I am going to show you how to do those questions on your calculator whenever there's like a little calculator symbol. For example, I'm going to put the first problem up here. You're given f of 2 is 5 and f prime of x is equal x plus sine of x. And you want to find f of 4. Okay, so again, this is what I'm saying, like this value is going to change. My starting value that you're given is not f of 0 this time, it's f of 2. So when I'm writing out my formula, this would be f of 4 is equal to my starting value of f of 2 plus, I'm starting at 2 and I'm going up to 4 of my function f prime of x dx. Okay? And then from here, you just have to evaluate this. I haven't taught you yet how to do this stuff by hand, so we need to use a calculator to solve it. So what you're going to do is you're going to plug in this information on your calculator. This is 5, and then you can type the integral from 2 to 4, and then we're given here the derivative function, so I can go ahead and put in x plus sine of x dx. And if you type this whole thing into your calculator, it's going to end up giving you the answer of approximately 11.237. Now, a few things. You have to be in radians. Okay, if you're not, you will get the wrong answer. To get to the integral button, you can do two things. You can hit math, option 9 on your calculator, or you can hit alpha window, and that's option number 4. So double check when you type this whole thing in the calculator that you get 11.237. And if you can't get that, let me know and I will help you figure it out. But that is, I think, the only thing on your homework that I need to tell you right now for figuring that out. Okay? So let me know if you have questions. You guys have the rest of class. So you got almost like, what, 40 minutes to work. So you'll for sure at least get one of those assignments done.
Two anyway.